Um, so we have the pleasure of having two great speakers today who are going to talk about the sort of mysteries of stellar populations in globular clusters, how they might or might not be enriched and form multiple populations, and all of the details there. And so first we have Even Cabrera Ziri, who's a Hubble Fellow here at the CFA. And did a PhD in Liverpool at John Moores University. And then we're going to hear from Jill Manning, who's coming like this from sort of a theoretical side, and she's now an ITC fellow here at the CFA, and before that did her PhD in Santa Cruz. So, Even, take it away.
Okay,
Thank you.
Okay, well, yeah, it's a little bit loud. Okay, so let me first talk a little bit about the globular cluster multiple populations and why we care about whether or not these clusters in general have gas or not. So when we looked at globular clusters in the past, or 20 years ago, we found that they had no iron spreads. If you look at the CMD, everything is consistent with the nitrogen. So we thought that that they were born as a single star population. This is all the stars were born at the same time with the same chemical composition, and then they evolved passively through time, right? But then we got HST and very nice filters, and then we figured out that this is not true anymore, and it's a little bit more tricky. So if you see, for example, a UV CMD, you can split this globular cluster into several different sequences, and each of these sequences has a very distinct chemical composition. Okay, and the thing is that these different abundance patterns that we see here, they are only found in globular clusters. We don't see them in field stars. For example, field stars have this kind of composition. For example, like in these orange stars here. However, in globular clusters, we find that these abundance variations are significantly different than in the field. And they are very peculiar to globular clusters. We don't see them in open clusters or in the field stars. So people is trying to figure out why globular clusters evolve this way and have this kind of chemical footprint. So the key properties of this problem are the following, at least for what I'm going to talk today, is that these abundance variations that we find in globular clusters resemble very much what you get when you burn hydrogen at very high temperatures. These are the ashes of what you get when you burn this through CNO cycle at very high temperatures. The other key thing is that most globular clusters, with a section of a handful, they don't show any iron peak element spread. They are all consistent with a single value of iron. And we also found these chemical anomalies in all evolutionary stages. So this means that it's not something that the stars self-enriched. So this was something that the stars had when they were born. At least this is consistent with this idea. I told you already this. The last point is that we don't see this in the field or in low mass open clusters. So this suggests that you need something like a very dense and massive environment to undergo this kind of chemistry. So the idea is very simple of most of the globular cluster formation scenarios. So you have these first generation stars, then the ashes of this high hydrogen burning is going to be ejected into the intercluster medium. This is a very low velocity wind, so it's going to be hauled into the cluster potential. And then you're going to form a second generation stars with the ashes of this first generation. So you're going to have this chemical signal that we only find in globular clusters. And then the cluster is going to evolve with these two different star formation bursts with which each of them have this unique chemical composition. So I'm going to start showing you the constraints that we have found using young massive clusters. These are clusters that have the same masses and densities as globular clusters, but they are significantly younger. And we can use them because most of the scenarios don't make any distinction between the formation of clusters and star formation in general in high redshift compared to a local. Yeah.
You know, when you were saying that you saw the gas, the model would have the gas ejected at low velocities, what about supernovae?
Yeah.
I mean, I would imagine that unless you are assuming that there's a special initial mass function, that there would be massive stars, and that these massive stars would exist in fairly large numbers, and that they would have a very high velocity.
Sure. So that's a very good question. So the key here that we care about the low velocity winds is because we don't see any iron peak variations in globular cluster stars. So all the stars have the same iron spread. Okay. So if you manage to retain a globular cluster supernova ejecta, then you will have an iron spread within the cluster, which is inconsistent with what we see. So all these scenarios are very timely designed to only act on what you expel on these high mass stars. We don't need, if we get supernova, we don't get the chemistry right that we see today.
In other words, there's special conditions so that all ejecta from supernovae escape.
For most of the clusters, this is the case. Other than a handful, the most massive ones, which perhaps this was the case, that we see an actual iron spread. But the overwhelming majority of the clusters, they don't. So this supernova retention might be the case for a handful, but most of them.
I'm sure you have. I don't want to hold you up because I'm sure.
No, don't worry.
But
So we can go.
I'm curious though about eventually, maybe toward the end, how does it physically? This must correspond to very special initial conditions.
I think Jill's talk will
Yeah.
focus on that a lot, so we can have that conversation again. Yeah.
Yeah. Okay. So so I was saying that they don't make any distinction between star formation and cluster formation in high redshift to what is going on in the local universe. So in principle, we can use what we see today to constrain the formation of globular clusters. So I'm just going to start going through the evidence of what we have found when we look for gas reservoirs in young massive clusters. These are, again, systems that have the same masses and densities as globular clusters, but they are just forming today. Okay. So we have a bunch of predictions from different models that tell you when do we expect to see the gas reservoirs, what are the masses of these reservoirs, which is the profile of the gas reservoir, etc. So we can look for these predictions, right? So first I'm going to show you some results we got from ALMA looking at young massive clusters in the overlap region of antenna. So we have these three guys over here. They are very massive, 10 to the 6 solar masses, and they are in the age range where we expect to see them hosting these huge gas reservoirs within them. Okay. The thing is that when we look at the spectra, we don't see any gas there. Okay, we can place an upper limit of 8% of the stellar mass, which is below what the predictions of these scenarios. And so this is one constraint, but then some people said perhaps the gas is a little bit warmer, so you're not going to see it in this phase. So you need to also look at for warm gas. And then it's eventually going to cool down and form further generations of stars. So people have also looked into this. So here we are looking at some study that study 13 clusters in this same age range where we expect to host these gas reservoirs. They are also massive, like globular clusters today. And they didn't find any H1 within them. And when you look at the dust that we expect to be associated with these gas reservoirs, they have, so here are the stars, and here in these columns is the dust, and there's no match within them, okay? And they can place an upper limit, these guys, of up to 1% of the stellar mass, which is in the form of this gas reservoir, if it's actually there. Again, none of these clusters were found to contain gas or dust. But people also looked at, instead of the dust emission, the dust absorption. So if you take the profile of the predictions, the gas profile of the prediction, and then you use a recipe to see how much dust is associated with this gas, and then you turn this into an extinction map, you expect to see within the very course of the clusters a lot of attenuation by this gas. Okay, you're going to see something like 8 or 3 magnitudes of extinction if these clusters were to host a gas reservoir. However, most of the clusters don't show this. Okay, they are very they have very little extinction. So the thing seems to be that since very early ages, we're talking 4, 3 million years, 2 million years, all the clusters seem to expel all the gas that they were from they were born. So in these images, you're seeing H2 in red, and these are bubbles going away from these clusters. And you see that this is independent of the mass of the cluster. You see it here in these 10 to the 4 clusters. But then we can look also at something a little bit more massive. It's 10 to the 6 solar masses, and also very young. The radius like a globular cluster, the metallicity like a globular cluster, very metal poor. And the cluster in the core has a very little extinction, so it's no gas reservoir. And if you work out how much with the velocity of the shell that we're measuring, you can work out when did it start to expand, and then you see that this cluster in particular is very likely to start ejecting all this gas from 3 to 4 million years ago. So as soon as even before some of the supernova go off, okay, they seem to be gas-free. So wrapping all this up, it looks like these young massive clusters are not able to retain gas. So this is why we don't see any multiple star formation events. So a lot of people have looked at the star formation history of these clusters, and they are all consistent with a single stellar population, okay, with no age spread. So after all this, you can say, well, perhaps we require special conditions in the high redshift, right, to have all these different multiple star populations within clusters. Even more, I never show you anything about whether or not these guys are actually globular clusters, if they show the same abundance variations. So I'm going to plug shamelessly the results of our latest survey. This is an HST survey of clusters in the LMC and SMC, where we see that the chemical variations are happening since 10 gigayears all the way down to 2 gigayears, okay? So there's nothing special from the early universe, okay? So this is still happening today. We have non-detections of these chemical variations in ages younger than 2 gigayears. They might be there, but they could be like very, very, not as severe as these guys, so we don't see them. So let me show you an example. So this is the youngest target in our cluster, in our survey. So here I'm showing you a V minus I CMD, which is not sensitive to chemical variations. So here I'm showing you the two different stellar populations in this cluster. In this CMD, where you see the distribution along this ridge line, they all lie within each other. However, if you use the special combination of filters and filters sensitive to nitrogen variations, you're going to see that all these blue and red populations that were on top of each other, they separate. So the red stars are preferentially to the red, and the blue stars are preferentially to the blue of the RGB. And this is significant. And just we got a spectral confirmation of these guys, of the abundance variations. Again, this U-narrow filter is sensitive to nitrogen variations. We have the spectra, and all the stars have the carbon, the same carbon abundance. So what is changing here is the nitrogen. So we see these changes in the spectra. So it's not a systematic effect of the observations. It's a real thing, detection that it's a real signal that we are seeing. And to put this into context, we're talking about something that formed at redshift point 17. So it's basically today. And we got this paper accepted yesterday, where we got the star formation history, and we put an upper age limit of any age spread here is at most 7 million years plus minus 16, which is consistent with the age spreads that we find in young massive clusters forming in the galaxy. So again, all this is this is consistent with the picture I showed you earlier, that the clusters are gas-free, so they cannot form multiple star formation events. So this is a summary of the talk. So globular clusters, young massive clusters are the same thing as globular clusters. They are gas-free from very early ages, regardless of the mass, metallicity, or environment. We see this in merging galaxies, in dwarf galaxies, metal poor, metal rich, etc. This is at odds with the predictions of most of the scenarios, where we don't see any gas reservoirs from the stellar ejecta, and we don't see any reaccretion going into the clusters. And this is also consistent with that we don't find any extended star formation events within these clusters. So I'm just going to stop here, take your questions, and see. Okay. Yes?
So what's the status of the thought that mergers could be responsible for these changes? I know you said that there weren't, for the field stars, there weren't these separations, but then some of the effects look pretty subtle to me, and so clusters would be a better way to see these subtle changes in field stars.
Sorry, I'm not sure what do you mean?
What's the aspect? People looked at whether merging could be responsible for these.
Two cluster merging, one with one chemical composition and the other one. Okay, that's a very nice question. So let me, I don't think I have any, okay, yes. Let me just go back to the first slide. Okay. So maybe we have a cluster with this chemical composition and a cluster with this, so we merge them and then we have, okay, that's one possibility. However, there are no clusters with just this kind of chemical variations, okay? So this doesn't happen. So they always go from here and then they start spreading this way, but we never have clusters with only stars here, okay? So it's always like this. So it's not like we have this kind of cluster and this kind of cluster and we merge them. So it's always like you cannot create this kind of trend with this. Yes?
So do you think that the gas is ejected by pressure from H2 regions, like about 10 to the 4 Kelvin gas, or is it supernovae?
Yeah. I'm an observer and I don't know much about feedback or the details, but I'm sure you can.
I think since the gas is moving at above 10 kilometers per second, it has to be a combination of other things, of radiation pressure and maybe wind and stuff like that. Because we would expect that if it was just an H2 region expansion, it would be 10 kilometers per second. Right?
Could be a little higher.
Yeah, that's like 4 times higher.
Yeah.
Or maybe Jill does.
Well,
Any more questions for clarification now? And then we'll have time to talk with all the bunch speakers together about some of these big questions. Great. Well, let's thank you, Jill.
No, I think I can just HDF one. Yes, Well, let's not get carried away. I'm only a theorist. Okay, so in answer to maybe some partial answer to some of the questions that came up. So I'm going to be talking specifically about the effects of stellar winds and how there's an interplay between kind of how you assume these winds thermalize and how much material is ejected from different kinds of possibly protoglobular clusters. No, maybe?
where did that science come from? Is that real or did you make it?
The internet. It came from the internet. Okay.
Oh, the internet is one of okay. Thought maybe you
Okay.
drove off the freeway. and
There we
stuff.
go. No, yeah, that would be bad. Okay, so just a few questions that a theorist maybe can answer. So how much material do we expect to see in old stellar populations like globular clusters? Was there a point in time where they had more gas? What kinds of clusters are either conducive to losing a lot of material or keeping a lot of material? How does it depend on the population age and things like the mass and radius of the cluster? And specifically, for what I'm going to be talking about, when can stellar winds either aid in retaining material or expelling material from the cluster? So, of course, our previous speaker went through a lot of this, so I'll go through it pretty quickly. But just a reminder, there are, usually when we're talking about multiple populations, we're talking about it in different kinds of clusters, so young, massive clusters, intermediate age clusters, and globular clusters, and they have different ages and relative masses. Again, this was already covered, but basically we don't see a lot of gas in most of these clusters. So that's something to keep in mind. And that I'm only going to be talking about stellar winds, but there's actually many possible methods to clear gas at different times. So there could be UV radiation, there could be supernova at different times, and there can also be compact object accretion, and many things like this. So again, I won't be talking about this, but these are also things to keep in mind. And again, so we see multiple stellar populations in globular clusters, and the weird populations are a sizable fraction, right? So you have, in some places it's about half and half, with these weird abundance anomalies. Also, I'm going to remain agnostic about this, about if they see stellar populations, multiple populations in different age clusters than globular clusters, especially because one of the authors is here, so I'm not going to get into this, but but just to say that there's differing opinions on this. I recommend that you read these set of papers with like a glass of wine or something. And again, if you see the previous talk, right? So there's also varying abundances in some of these systems. And so the natural question, of course, is this a path to globular cluster formation? Do you go from young massive clusters to intermediate age clusters to globular clusters? And so there's a few different scenarios, and a lot of it depends on what happens when, so I'm just going to go over those. The previous speaker went over this one, so basically you have something like AGB winds plus external gas, and those things are retained in the cluster, and then that forms a second generation of stars. And so the basic timeline is you have some clearing by something like supernova, maybe. Then you have the return of material over a few hundred megayears to a gigayear. Then you have another process that clears the gas, and then most of the stars are lost, so that you have these, or most of the first population of stars are lost, so you have these equal ratios between the weird anomaly stars and the first generation. There's also early disk accretion and fast rotating massive stars, and basically the idea is that Supernovae don't actually clear all of the material. Even, there's some arguments for you clear enough so that you don't get, these, you don't get any iron ratio anomalies. I'm not going to get into it. But basically, the basic idea is you don't clear all of the gas, you retain that gas. You have a first generation of massive stars, though they pollute the background material. Less massive stars are still forming, and they move through this material. They accrete some of it, and then that is what leads to this abundance anomalies. And again, different heating mechanisms can be important at different times. So for young things, you have supernova, you have high mass stellar winds. For medium things, maybe accretion onto compact objects, maybe some AGB winds. And then at later times, sort of fast RGB winds that I'll talk about a little bit, maybe pulsars, things like this. So in the interest of time, I'm not going to get into this over much, but basically there's two ways you can attack this problem, either 3D or 1D. I mean, I guess you could do 2D if you really felt like it. I think some people have. Basically 3D, there's a lot of people looking at this. So people have done sort of detailed simulations of individual clusters losing mass so they can actually resolve individual stars. Some people have done, where's the pointer? Hey. In the context of moving through some background medium, right? So you put in some stellar winds, you move it through the background medium, you see how much you can retain. Of course, the issue is you can only resolve a few stars. So for example, this is a project I'm doing with a student, and we can only resolve about 50 stars. I think this has maybe 50 to 100. And this has some prescription for stellar wind loss. So you can only resolve a few stars. You can't do all of them. And also these things are relatively expensive, so you can't run a suite of different masses and radii of different clusters in different situations. And you sort of have to play between resolving the cluster, the large-scale structure like this simulation, or resolving individual stars. So that's one issue. So I'm going to be talking about stuff that we're doing in 1D and sort of some of the issues that come up with that. So here's basically just the fancy written out conservation equations. And the things that you should be aware of is basically these take in a prescription for some addition of mass from stellar winds and some addition of energy. And of course, you have the acceleration from gravity from both the gas itself and the potential well. And also, you might want to take into account some heating or, sinks of heating, like a cooling function. And so basically, we need to pick the total mass injection by a population of stars. And here we're going to use as a proxy just some average mass loss rate times the number of stars. You also have to pick the, and also how these things depend on radius. For the things that I'm going to show you, they're just going to follow the potential. But of course, if you have more material being lost more centrally, then that can help aid in retention and things like this. And this is, of course, a function of time, with different stellar populations having different mass loss rates. And also the energy injection, we're going to take as a proxy the average stellar wind of the stars. Also, of course, we're going to have to make some assumptions about the potential. What I'm going to show you is just uses a Plummer potential, because theorists like it. It's easy, it's analytical. And we're also going to include the effects of self-gravity, cooling, and for star formation, we're just going to follow it until it collapses such that the dynamical time is less than the sound crossing time, and not actually follow the detailed star formation, but that's something that potentially you could do as well. Okay, so it turns out the hinky part is picking out the average mass loss rates and average wind velocities for stars. So what are those things? So there's two questions. So what is the mass loss and wind velocity of an individual star, and how that depends on the star's mass and how old it is? And then what is the mass loss and wind velocity of a population of stars, right? Because we're doing these average things in 1D. So first, let's ask this question. So specifically on the AGB branch, but also in other branches, the detailed instantaneous mass loss rates are not very well constrained. So these are a few different models, and you can see that there's all of these. This is a thermal pulsing AGB branch, and so when and how those pulses happen is very different, and also the yields from those things are contentious as well. And on the main sequence, you'd think it would be better, but you'd be wrong. So here is basically a compilation of observations of mass loss rates along the main sequence for different masses of stars. And here I'm highlighting the changes in the solar mass rate. So this is predicted over the lifetime of the sun and also with X-ray activity, right? So there's these big changes on the main sequence itself. And I'm not going to go into detail about the stellar evolution models that we're going to be using, but just know that they're MESA stellar evolution models. And that's the line predicted from MESA, right? So, it's pretty good, but there's these huge variations, particularly, for one mass, you can get something like 4 orders of magnitude in variation. So that's sort of problematic. So what can we actually constrain? Well, we can constrain the total mass loss from a given star. So here are some observations from a few different groups. And then, we can show, oh, look, our MESA models, fit that well. But the instantaneous mass loss is sort of difficult. Okay, so the wind velocity from a single star. I'm going to try and motivate that now we have to worry about a factor of 2 in astronomy. And I apologize profusely for that in advance. So, okay. So usually people say, along the AGB and RGB branch, the, wind velocity from these things is on order of 10 to 20 kilometers a second, right? And so here's a slide that I've brazenly stolen from a talk by McDonald. And you can see the different colors are for different wind velocities. And so you have things in blue. So these things are, 10 to 20 kilometers a second. And that's from mainly H alpha measurements. And then from helium-1 lines, we have something a little bit higher, more like 40 kilometers a second. And so here's sort of a compilation of observations. So this is, again, wind velocity and in log on the x, and then luminosity on the y there. And then these funny little histograms are from our MESA stellar evolution models. So those are the ranges over the lifetimes of those stars. And they're weighted by the change in mass. And so there's sort of these two groups of observations you can see, and they come from different places. So here is a model of an atmosphere, and so radius goes that way. And so this first group is from the H alpha measurements, and so this is sort of deeper, deeper within the core. And then as we move out, we get to the helium-1 lines. And so these are this other group that lies more closely with our stellar evolution models. And so basically, you don't have to read this whole thing. The idea is that people can observe at these different points in the atmosphere. And so they don't see any inflow. They see no inflowing gas. And so if you have something that is, moving slowly on the inside, faster on the outside, it's probably accelerating. And there's no reason to think why it's not going to just accelerate until it reaches the escape velocity of the star, especially if you see no inflow. So this is why for our models we're going to assume that the stellar wind velocity is something like the escape velocity. So this is, again, a little bit higher than what people normally assume in their models. There's a bunch of caveats. So there's a lot of ways you can think of maybe getting at this lower velocity material. And if you assume that that thermalizes, this means a lower temperature material. So things like ramp pressure stripping. So if you have something that's a red giant or an AGB star that's moving through some background medium, maybe it can get stripped and you can get to these lower layers. Also, you can have stellar encounters, and maybe that rips up some material lower on. And also, again, if you're on the thermally pulsing AGB branch, perhaps that can remove some lower velocity material. Okay, so we talked about the first point. The second point, now we have to worry about, for a population of stars, what is the average mass loss and wind velocity. So here is a plot of the mass loss rate along the HR diagram. So again, this is 12 orders of magnitude, I guess, in variation at different points, where the main sequence here is sort of generally outlined in a gray. And so you can think of this population is going to have overall mass loss rates that are different at different times. So at birth, it's going to look a little bit like this. Then you get some more high mass stars ejecting a lot more hot material. And then when it gets old, you're going to have a population that have high mass loss rates but are ejecting at a lower wind velocity. And so how do we represent that? So again, glossing over the details of the models that we're using, they're MESA stellar evolution models. But basically, one idea that was put forth by Pooley and Rappaport a little while ago was that you can represent the stellar population by the turnoff star. And you take some averages over the mass loss rates and wind velocities from the zero age main sequence to the AGB branch. And so this is sort of nice because periods with higher kinetic energy are sort of contributing to the dynamics more. And so for an example, if you have something that's about a solar mass, your average mass loss rate is 10 to the negative 11 solar masses a year. Your average wind velocity is something like 55. Where again, you have much higher mass loss rates on the RGB branch, but this is averaged over the lifetime. Okay, so that takes care of sort of the evolved stellar population in this HR diagram. But what about all of the things on the main sequence? This sort of ignores that a lot. And so, I mean, you could say, well, you know, the mass loss rates are much, much lower. But it turns out the wind velocities are also much higher. And so if you look at the ratio of the contribution of mass loss rates from turn-off stars versus main sequence stars, you can see that this is, you know, ratio of the relative number of stars. Basically, turn-off stars tend to dominate the mass. However, if you do the same thing for the kinetic energy, you can see that they both can contribute. And this was an idea put forth by Smith. I think there's also a 2004 paper. And this is assuming some effective thermalization between these populations of stars. So unfortunately, this is another factor of 2 that we have to worry about. And so what do all these factors of 2 mean? So if we look at the velocity dispersion of globular clusters and young massive clusters and intermediate mass clusters, you know, this is something tens of kilometers a second. So if you assume that you have just these low winds, right, you expect to retain that material. But if we multiply by both of these factors of 2, you have the stellar escape velocity factor and also the main sequence heating. Now you have a problem. You're expecting to eject a lot of things. And so we can do simulations with both of these prescriptions. So you can see, for example, that at different times overall, if you just use the turn-off star, you have a relatively low wind velocity compared to if you average over the population. And so these are different times, and so we can do simulations of our clusters in 1D at those different times. And the takeaway is that the population average things tend to have higher wind velocities and higher temperatures, right? So those are these, the dashed lines compared to the solid lines, and also things that are young, which is A, so the pink stuff here, and also things that are older, which is C in blue there, tend to have higher gas temperatures and tend to eject material. But there could be a sweet spot at these intermediate ages to retain some material.
Population average means the ones where you include the
Main
kinetic
sequence.
energy.
Yeah. Okay, so 1D simulations, I've been talking them up. The nice thing is you can get some parameter space, so let me give you some parameter space. So here is a suite of simulations. These are the final retained gas masses as a function of both age and for different velocity dispersions and masses. And so again, there's different populations that these cover, and there are different things that we haven't taken into account, right, in these different situations. So keep that in mind. And here, this is, again, for the Trump prescription, you can see where we expect to form stars in our simulation, and that tends to overlap between some regions of high material retention. However, for the population average prescription, where we include the kinetic energy from the main sequence, those regions are offset. And so what does this mean if we look back at our sort of path to globular cluster formation? How does all this stellar wind stuff relate, except for just kind of being a downer, right? Well, again, if we look at, which is true, it's a fact, it's kind of a downer talk. So if we look again at the different ages, and we can ask, so we said that there's no gas, with a few exceptions, and we look at our population average prescription. For globular clusters, we don't see any gas, so that's great. And for young massive clusters, we don't see a lot of gas either, so that's great. For intermediate age clusters, though, we predict that maybe there should be a lot of material. It shouldn't be forming stars, but maybe there could be a lot of material there. So luckily for a theorist, right, it's actually very hard to measure for a variety of reasons. So you'd need to detect gas down to these levels. You'd need pretty local observations, and if you want to detect star formation, you need to get even higher precision measurements. There's also, you have to take measurements over both the near IR and optical to actually resolve the different stellar populations, and also you could maybe think about looking in merging galaxies, but I've simulated here retention in isolated systems, and so these aren't really isolated systems in merging galaxies, right? They're surrounded by other material, and so that's not really going to work. So I'm going to give it a theorist check because, until somebody actually takes observations, it's fine. And of course, there could be other heating mechanisms there that we have not taken into account at all. So that's another thing to keep in mind. What about star formation? So for, again, efficient thermalization between main sequence and evolved stars, we don't expect a lot of star formation. So that's good. And what does this say about the formation theory? So again, one was the sort of retention of AGB winds, so stellar winds, and the other one was accretion during formation from a background of material ejected by massive stars. And so basically, either way, if you, again, we're remaining agnostic, so either way, you're going to have this background of relatively hot gas, hotter than people were thinking. And if that mixes with whatever gas from whatever system, or whatever theory you think is supplying material for the second population, this is going to hurt retention. With the caveat, again, that we're doing things in 1D, and so if you do things in 3D, you could have a situation where you have hot materials flowing out of the cluster, and then you're able to keep some sort of reservoirs of cool gas as well. So that's one thing to think about. So that's it. Thank you. Yeah.
Two questions. One is just a technical one, which if you have time you can show us. I was a little confused about the Mesa models because it didn't look as if they did very well, even in the first image. That, most of the actual data points seem to be below them. So I had a question about that and whether when you use them, you use them raw or you make a correction. But my main question actually had to do with your very nice point about going from the young clusters to globular clusters. I guess you're right.
Yeah, no.
Yes, there you go.
Yeah, I mean, so here we could. Yeah, I mean, so it's not. Yeah, here we sort of overpredict the mass loss a little bit. I'm not showing any error bars, so that's another thing to keep in mind. Yeah, I mean, this is it's a very basic prescription that we're using for the stellar wind mass loss on the main sequence. There's not really so for sort of the more evolved phases of evolution, there's a lot more study into what the mass loss prescriptions might be. But on the main sequence, nobody cares, turns out. So we're this is our best guess of what's going on, and so clearly we're doing not as well.
I was just curious about it.
Yeah.
It's an important thing to know about MESA if you're doing this, because there are cases where, let's say you have a 10 solar mass star, and it has a companion, which may be a compact object. That's a situation where you're very interested in whether it's, 10 to the minus 8 solar masses per year or 10 to the minus 10.
Yeah, so
in terms of the phenomenology in that case.
Yeah, so for higher masses, people tend to do a little bit better. People care about those stellar winds. So there's newer MESA stellar models that we're using for a follow-up paper that do a little bit better than this. But these ones that we're using is not. We haven't done as good of a job as we could be. So we basically just put in the prescriptions that people typically use for stellar mass loss, and this is sort of how it turned out. So yeah, there's definitely, this is a thing, that, especially at the high mass end, that people are still working on as far as stellar mass prescriptions. At the low mass end, it doesn't seem like people care as much about it.
Well, I guess that the rates are really pretty low, so their effect is less important. But my main question, which maybe we should leave for the discussion, is this issue of going from the young clusters to the globular clusters. And, one thing that you might think is that since the young clusters anyway, and if we go to a little bit older, the ones that are open clusters, these aren't good candidates to ever be globular clusters. So maybe, what is the benefit of starting elsewhere? For example, we know globulars form in places where you have galaxy mergers. So maybe they started in a different way, and then calculations like yours with different initial conditions might be able to solve the problem. Is that something that people are working on?
Yeah. So again, this is just sort of the very simplest model that I showed you. But you could think of, if you're surrounded by gas, then maybe you have some pressure confinement. So people are looking at that. But then if you're moving, at Mach of a few, if you have all of this gas in your center and you're moving at Mach of a few, then maybe you can strip some of that gas. Maybe if you take hotter wind ejection plus stripping, and then you get rid of a lot of the gas. So it's there, especially in 3D. There's people that are sort of playing around with that parameter space. But
Interesting thing to discuss.
yeah.
Well, I would propose that we thank Jill and then pause for 2 minutes, get pizza, and then come back to your seats and we can ask all of our pressing questions.
Yeah. Is it this thing?
This is just of these global properties, but if you look into the abundances and try to figure out what's going on there, it's a mess.
So from your discussion of the antenna clusters, so then would you say that the young superstar clusters are forming the same way as the old globular clusters did? Just a single burst of star formation in the antenna clusters?
Yeah, so we have no evidence otherwise. To convince you? Yeah, sorry.
You're welcome.
I have a question for Jill. The HR diagram that you have, it's a beautiful, very comprehensive result. I saw that the mass loss rates went all the way from the low value 10 to 4 mass, 4 solar masses. But in supernovae, we know that there are some stars which have mass loss rates which are extremely high. So, what happened?
So you mean in the supernova process, you mean the pre?
Right, the progenitor had a very high mass
and
loss
then
rate.
mass loss.
It can go all the way to like 10 of solar mass.
Yeah, I mean, it's just, that's not like a comprehensive, it was just sort of kind of more of an illustrative diagram of how things can change on the HR diagram. But I mean, it could definitely be updated.
So what is the fastest way to drive the mass out? So you've got, if you want to have a single episode of star formation, then you want to get rid of all the gas fairly quickly. And if you're doing it with stellar winds, say, is that going to be slower than, say, for example, by ionizing all the gas and driving out gas pressure? Or
I think
if you wait for supernova to evolve, what do you think about that?
Yeah, I think you don't require supernova because of the timescales that we're seeing. Clusters being gas-free already 2 million years. But what is going on there? Maybe she's better to answer you. Maybe it's the radiation, I don't know, it's the ionization, I'm not sure.
Yeah, I think it's probably a combination of them. But
Probably. I mean, for winds, the energy, the kinetic energy injected is similar to what the supernova would eventually give you. Since they're very densely packed, right? So they're probably radiation pressure dominated. You have to like do the analysis to. So radiation pressure, at least early on, might be more important than ionizing or than the warm gas pressure. But it's probably a combination of all the feedback effects. Also, like winds can get out like low density material and stuff. But I had a question about that too. Like, so the fact that you're seeing all these like young, massive clusters with all the gas out. So do you get star formation efficiencies for those? Like, can you say that the gas?
Yeah, I think some people have worked on this. I don't have the numbers here, but I understand that the most massive ones are the most efficient.
Yeah.
And they kind of collapse, and in the inner bit, they're just burn everything put everything into stars. The lower mass ones are a little bit less inefficient and they take longer, etc. I don't have precise numbers.
Yeah, I just wonder. Yeah, because if you have really high star formation efficiencies, then you can keep them down. And then, so I wonder, because I know a lot of people on the papers, like on the cluster disruption debate. What do they think about these types of clusters? What did you mean?
Yeah, yeah. I don't
Like,
want.
are these bound? Like when you look at the stars, they're. I mean.
All these guys that I show you are bound and going to be bound for a while. So
Okay.
yeah, so there's no. It's very unlikely that they maybe the where's the.
And it's because the presence of star formation efficiency is so high, the gas removal is so rapid that it's high enough to keep it down.
Yeah.
So those young clusters are full of OB stars, and so certainly there has to be a bunch of supernovae that are going to go off. So, I mean, you said a moment ago that you didn't need supernovae to drive away gas, but if you believe that those are the analogs, then they're going to happen whether or not you need them. So somebody studied what the impact of that is on.
Yeah, so if the cluster is already gas-free, and then you have this supernova going up, the wind is just going to escape, and you're not going to self-enrich the stars. So it's very inefficient just to throw gas into a star and accrete into it and change it, because the cross-section of the star is very small. So you need like disks, and this is what the early disk accretion was.
But how can these already be gas-free if they're still forming stars?
Why they are still forming stars?
Well, if they have OB stars, I mean, they formed stars in the very recent past, so.
Yeah, so let me just, maybe this will help. So we're not talking about old clusters, we're talking things that are 3 million years, 4 million years. So these are consistent with a young star formation event, right?
Yeah.
And this guy over here even have Wolf-Rayet features. So you know very precisely the age of this cluster. So the supernovas are going to go off after this, and then it's going to evolve like passively. So you don't need to make it more.
Are you asking about what the effects of supernova would be? Like, is someone looking at the gas clearing effects of supernovas?
I guess in part.
Yeah, I mean, there's a few people that are looking at both supernova type 2 from like the young population, and also for less massive clusters, supernova 1A. Yeah, I mean, so there's some studies where people, so if there's no gas, then nothing really happens. Some people say if there's a lot of gas, then you might not be able to clear all of it with supernovas. So I think that's L-E-I. Anyway. So people are looking at sort of those simulations of those kind of mechanisms as well. But I mean, at these times.
Yeah, but the thing is, you don't need to worry about this because clusters are gas-free. So if you just explode as a supernova, then the gas is going to go away, and the stars, they don't care about this.
I'm thinking of all of the implications, I guess, of having these massive stars around. I guess my last question is, what evidence is there that old globulars had this population of OB stars? Or I guess maybe another way to put it is, what evidence is that they had the same IMF as these massive clusters?
So people have worked it out. So we're only seeing stars of about 1 solar mass or less, right? We're 0.8 solar masses of a globular cluster. So from the stars that we see, they are consistent with a normal IMF after you account for evaporation of stars and mass aggregation and dynamical effects. If you account for this, they match what you expect from a normal group IMF or whatever. But the high mass end, I don't know, we will need to look at, I don't know if there is a signature from the white dwarfs, if we can tell them apart, I wouldn't know. Andrea, I think you were...
Yeah, I was going to say, we were intrigued by a suggestion that Alvio Renzini threw out a number of years ago, saying that really the second generation are Mont-K stars, and that what's happened is they've accreted all this material from, let's say, the red giants or the previous stars. And when you actually look at the fast winds that are coming out of the red giants and the mass loss, they can accrete onto a main sequence star, and maybe that's how some of the gas is recycled or recirculated.
Yes, this was proposed with this early disk accretion model. Here, the idea is that you have a star cluster, then all the stars were born at the same time, then you're going to have some winds of whatever, pick your favorite polluter. Then you're going to treat this material with a accretion disk of these main sequence stars, the same stars that we see in globular clusters today. And this will put get the chemistry into the stars. However, there have been some simulations of clusters of a disk going into this gas reservoir, according to the recipes that people require. The thing is that you're going to destroy the disk as soon as you get, or very quickly, in a few million years, less than a few million years, when you hit the gas, okay?
Yeah, but he's also talking not from the very early stage of star formation, but like the red giants, like in the old clusters right now.
No, it's extremely inefficient. So bonding Hoyle accretion, you require the cross section of a normal star is not enough to get this in the whole time scale.
You just wouldn't be able to pollute it enough.
I'm
Yeah.
sorry?
You wouldn't be able to pollute it enough.
Yeah, you cannot strip enough material with the radius of the star. No. So this is why you need the protoplanetary disk, AUs of
To
cross
get
section.
more material.
And even then, you're pushing it with the mass budget column and all that. So just stripping into a star is extremely inefficient.
Okay, so what's the answer?
We don't know.
You just told you why nothing works, so.
Yeah, and we are looking into this chemistry, and it looks like it's even worse than before. So, yeah, so this, remember I told you it looks like CNO burning, these ashes, these chemical variations. Now we find a population that is changing in helium, or we think it's changing in helium, however it's not changing in carbon and nitrogen and the other elements. So CNO cannot change helium without changing carbon and nitrogen, etc. Okay, so now we're just starting into a new kind of game. So we're making things worse the more we look into it.
On that optimistic
Yeah.
note, let's thank the two speakers.
Yeah, thank you, guys.
Fantastic
Yeah, thanks.
talk. And, help yourself to more pizza.
Yeah.